Hello, my name is Nolan Smyth and I'm a graduate student at the University of California, Santa Cruz, where I study the phenomenology of black holes and dark matter. Today I'm going to be talking about pulsar timing arrays, what they are and what they can tell us about the extreme gravitational events occurring throughout our universe.
Let's start by talking about one of the most exciting discoveries of the past decade, the detection of gravitational waves, ripples in the fabric of spacetime. Although originally predicted by Einstein's theory of general relativity, it was not until 2015 that the Laser Interferometer Gravitational Wave Observatory, or LIGO, announced the direct detection of gravitational waves for the first time. Since then, we have observed dozens of events caused by the merger of black holes and neutron stars. We expect that countless such events are occurring constantly. This implies the existence of a stochastic gravitational wave background that is permeating the universe. But such a background is more difficult to detect than the singular nearby collisions of massive black holes. Enter pulsar timing arrays. Pulsars are compact, rapidly rotating neutron stars. They emit electromagnetic radiation in pulses that arrive at Earth with incredible regularity, allowing us to use them as precise astronomical clocks. When a gravitational wave passes through Earth, it creates a difference in the arrival times of the pulsar bursts. Measuring correlations in arrivals across many pulsars, a pulsar timing array, allows us to make statistical statements about the strength and detectability of a stochastic gravitational wave background. With over 500,000 pulse arrival times recorded across dozens of pulsars observed for over a decade and counting, you'd be correct in thinking that analyzing all this data is no small feat. That is why, for the first time, we are applying machine learning techniques to the problem of pulsar timing analysis. In particular, we're working with an architecture called normalizing flows. In short, normalizing flows create a mapping between a simple distribution and a more complex distribution, typically modeling real-world data, through a series of invertible transformations. By allowing for exact likelihood evaluation and fast sampling, normalizing flows are a natural approach for performing density estimation. While that may seem rather technical, all we're really trying to do is learn the probability distribution of physical quantities. For example, we can use this technique to answer the question, how likely is it, given the data, that the stochastic gravitational wave background has a particular strength or amplitude? We are currently able to analyze the 12.5-year PTA dataset very quickly, providing efficient, unbiased estimation of the gravitational wave background amplitude and other physical quantities across a large range of the parameter space. We are now at the stage of refining our approach to reduce the variance in our output and ensure the scalability of our method as the number and duration of observed pulsars continues to grow.
I'd like to thank the ARCS Foundation for supporting this work, and all of you for listening to this brief talk.